Watch this. 5x plus 3 over the quantity x plus 1 times x minus 2 looks like one messy fraction, but it actually has two much simpler fractions hiding inside it. That is exactly what partial fractions lets you find, and we are about to learn how. So why does this even work at all? Any proper fraction whose denominator is built from distinct linear factors can always be split uniquely, because each factor contributes its own separate, independent term to the total. This is really nothing new, it is just the reverse of something you already know how to do. Add two simple fractions, say a over x plus 1 and b over x minus 2, over a common denominator, and you get one single combined fraction on top. Partial fractions simply runs that process backwards, taking the combined fraction and splitting it back into the pieces that made it. Here is that same addition, tilted so you can see the structure more clearly from another angle. The common denominator sits underneath both original terms, and undoing it means finding the two numerators, a and b, that would have produced exactly this combined fraction. Let's do a full worked example. Take 5x plus 3 over the quantity x plus 1 times x minus 2 and write it as a over x plus 1 plus b over x minus 2. Before we solve it properly, take a guess. What values of a and b do you think could rebuild this fraction? Multiply both sides by the quantity x plus 1 times x minus 2 to clear every denominator. This gives 5x plus 3 equals a times x minus 2 plus b times x plus 1. Substitute a convenient value of x to make one term vanish. Let x equal -1, so the term with b disappears entirely. This gives 5 times -1 plus 3 equals a times -1 minus 2, that is -2 equals -3 times a, so a equals 2/3. Now let x equal 2, so the term with a disappears instead. This gives 5 times 2 plus 3 equals b times 2 plus 1, that is 13 equals 3 times b, so b equals 13/3. So the decomposition is complete. 5x plus 3 over the quantity x plus 1 times x minus 2 equals 2/3 over x plus 1 plus 13/3 over x minus 2. Now what happens when a factor in the denominator is repeated? A single term cannot capture everything happening near that repeated root, because the fraction behaves differently at different orders close to it. So a repeated factor of power 2 needs two separate terms, one over the factor itself and one over the factor squared. Here is an example. Take 3x plus 5 over the quantity x plus 1 squared times x minus 1. This splits into a over x plus 1 plus b over x plus 1 squared plus c over x minus 1. Multiplying every term by the full denominator gives 3x plus 5 equals a times x plus 1 times x minus 1 plus b times x minus 1 plus c times x plus 1 squared. Let x equal -1, so both the a term and the c term vanish, leaving only b. This gives 3 times -1 plus 5 equals b times -1 minus 1, that is 2 equals -2 times b, so b equals -1. Now let x equal 1, so both the a term and the b term vanish, leaving only c. This gives 3 plus 5 equals c times 1 plus 1 squared, that is 8 equals 4 times c, so c equals 2. No single substitution can isolate a, since every value we picked always cancels it out. Before we finish it off, can you guess what a needs to be so that everything balances? Comparing the coefficient of x squared on both sides instead, since the original expression has no x squared term, gives a plus c equals 0. Since c equals 2, a must equal -2. So the full decomposition is 3x plus 5 over the quantity x plus 1 squared times x minus 1 equals -2 over x plus 1 minus 1 over x plus 1 squared plus 2 over x minus 1. Here is why any of this actually matters. Some integrals look completely unmanageable as one messy fraction, but once split into partial fractions, each piece integrates on its own, easily. Take the integral of 5x plus 3 over the quantity x plus 1 times x minus 2 dx. Using the decomposition from before, this becomes the integral of 2/3 over x plus 1 plus 13/3 over x minus 2 dx. Each piece is now just a simple log integral. This gives 2/3 times the natural log of the modulus of x plus 1 plus 13/3 times the natural log of the modulus of x minus 2 plus a constant of integration. That is the whole idea. One hard fraction gets broken into pieces simple enough to integrate directly. Let's lock in the whole process from start to finish. Step 1. Check the fraction is proper, meaning the degree of the top is smaller than the degree of the bottom. Step 2. Factor the denominator completely into its distinct or repeated linear pieces. Step 3. Write one unknown term for every distinct factor and two unknown terms, one for each power, for every repeated factor. Step 4. Multiply through by the full denominator to clear every fraction. Step 5. Substitute convenient values of x to solve for each unknown, and use coefficient comparison for any unknown a substitution cannot isolate. Step 6. Write out the final decomposition, and if needed, integrate each simple piece on its own. The single most common mistake is forgetting that a repeated factor needs two separate terms, one for the factor and one for the factor squared. Using only one term, there will always leave the decomposition incomplete. Here is the simplified version, essentials only. One messy fraction splits into simple fractions over each factor. Distinct linear factors each get one unknown term. Repeated linear factors need one term for every power of that factor. Substitute convenient x values or compare coefficients to solve for the unknowns. Once split, each simple piece integrates directly.